Hi students, in this video we're going to go over section 5.6 modular arithmetic. So our goal for this video is to discuss properties of congruence, modulo M, and modular arithmetic. The ideas that we develop in this section are based on the notion of divisibility. So division of an integer by a positive integer produces a quotient and a remainder. So working with these remainders leads to modular arithmetic. In some situations, we care only about the remainder of an integer when it is divided by some specified positive integer. So we have our definition for equivalence relation. There's that word relation. So a relation on a set A is called an equivalence relation if it is reflective, symmetric, and transitive. We went over those in the last video, those concepts there. One of the most widely used equivalence relations is congruence modulo M, where M is an integer greater than 1. So definition for congruence modulo M. So we let A and B be integers and M be a positive integer. We say that A is congruent to B modulo M, which we denote this way, if and only if M divides A minus B evenly. So symbolically, you can represent it this way. A is related to B if and only if A is congruent to B mod M, if and only if M divides A minus B. So example 1, we want to determine which of the following congruences are true and which are false. Okay, so part A is 18 is congruent to 9 mod 3, and we want to know if that's true or not. So that previous definition said that A is related to B if and only if A is congruent to B mod M, if and only if M divides A minus B. Okay, so in this case, this is my A here, that's the B, and that's this 3. So 18 is A, 9 is B, 3 is the M. So this is going to be, this congruence is true. And this is because the A minus B is 18 minus 9, which is 9. And your M, the 3, divides 9, divides that difference. That's a true congruence. Now we have part B. So we have 11, is that congruent to negative 1 mod 2? Well, if you subtract A minus B, you're going to get 11 minus negative 1, which is 12. And then 2 is going to divide 12. So this is another congruence that's true. So we'll put true because 11 minus negative 1 is 12, and 2 divides 12. Let's do part C. So we have negative 2, is that congruent to 10 mod 5? So if we subtract, we do A minus B, that would be negative 2 minus 10, that's negative 12. Does our M, the 5 in this case, divide negative 12? No, so this is a false congruence. So I'll say false because negative 2 minus 10 is equal to negative 12, and 5 does not divide 12. Notice I'm putting that vertical line that represents a division, but I'm putting the slash through it to indicate that 5 does not divide 12. All right, so I've done parts A, B, and C. Why don't you go ahead and try part D, pause the video, and just do it the way we've done the other parts, A, B, and C. So for part D, we have 4, is that congruent to 4 mod 7? So this one is true, and this is because 4 minus 4 equals 0, and 7 divides 0. consider a 12-hour clock, right? Something we're all familiar with. If it is 5 o'clock and time moves forward 4 hours, the hands on the clock show 5 plus 4, which is 9 o'clock. Okay, if it's 5 o'clock and time moves forward 8 hours, the hands on the clock do not show 5 plus 8, which is 13 o'clock. That does not show up. The hands instead show 1 o'clock. Note here that 1 is the remainder you get when 13 is divided by 12. We're dividing by 12 because there's 12 hours on the clock. So we're already, we don't think about it, but we actually do use this modular arithmetic when we think of a 12-hour clock. All right, a theorem here for modular equivalences. So we're going to let a, b, and m be any integers, and m here is going to be greater than 1. It's going to be positive and greater than 1. And then the following statements are all equivalent. So we already saw how 1 and 2 were equivalent in the previous definition. We also wrote it as a was related to b, right? So we know those are all equivalent. But 3 here is also equivalent. So if we have a equals b plus k times m for some integer k, that is how we can rewrite 1 or 2. It's equivalent to what 1 and 2. 4 is also equivalent. So if we have a and b, and if they have the same non-negative remainder when divided by m, that's a way of saying that a is congruent to b mod m. And a fifth equivalence, if you have a mod m, that's just equal. Notice the notation and the difference in sign here. A mod m is equal to b mod m. So these are all different ways of writing the same thing. So these are all modular equivalences. So just to kind of get used to them, example 2 here, we're going to let a be equal to 26, b is going to be equal to 14. Let's just explain why 26 is congruent to 14 mod 6. Okay. 26 is congruent to 14 mod 6. And I'll do this one the way we did the previous example. So I'm going to say that this is true because 26 minus 14 is 12, and 6 divides 12. Now for part B, we want to know what value of k has the property that 26 equals 14 plus 6k. So we have 26 equals 14 plus 6k. We're just solving for that k. So just use your algebra here. I'm going to subtract 14 on both sides and then divide both sides by 6. So k here would have to equal 2 for that equation. And that's like this one right here. That's like number 3. And then part C, what is the non-negative remainder obtained when 26 is divided by 6? When 14 is divided by 6? So when 26 is divided by 6, the remainder is some number, because, so you can show a little work for this, so I can say, I can actually do the long division. If I have 26 and dividing by 6, this would be 4. 4 times 6 is 24. The remainder I get is 2. So 2 is the remainder, so I'll just fill in that blank there. You could also, I'll put or, you could also write down that 26 is equal to 6 times 4 plus 2. There's your remainder there, that plus 2. And then run out of room, so I'm going to squeeze in over here. The rest of part C. When 14 is divided by 6, the remainder is what number? And then show a little work. What number would be the remainder? So I'm going to do the long division. Right, here we have 14 divided by 6. This would be 2 times 6 is 12. There's your remainder 2. And the remainder should be the same for both of these since these are congruent. So you can also, I don't have a part D here, but you can also think of it this way too. You could rewrite it, basically part C was number 4 here. You can also rewrite it this way too. A mod M is equal to B mod M. So you can write that 26 mod 6 is equal to 14 mod 6. That's another way of writing it. And then we have this modular arithmetic theorem. So we have A, B, C, D, and M. We're going to let those be any integers. M is going to be greater than 1. And you're going to suppose that A is congruent to B mod M and C is congruent to D mod M. And then A minus C is going to be congruent to B minus D mod M. And A plus C is going to be congruent to B plus D mod M. And then if you do multiplication, A times C, that's going to be congruent to B times D mod M. And if you use powers, exponents, A to the nth power will be congruent to B to the nth power mod M for all positive integers M. So that exponent has to meet a certain condition. So we'll go through, get kind of used to this. So we're just going to verify these following statements. So for part A, we have 24 is congruent to 4 mod 5, and we have that 8 is congruent to 3 mod 5. So we're just verifying those. So the first one's true, right, because 24 minus 4 equals 20, and 5 divides 20. The second one is true because 8 minus 3 is 5, and 5 divides 5. So that's my part B, just confirming those, verifying those. And then for part A, that was my part A. And then for part B, we're going to do 24 minus 8, that's congruent to 4 minus 3 mod 5. Let's check that out. So we have 24 minus 8, is that congruent to 4 minus 3 mod 5? Okay. So this was like the A, this was like the B, this was like the C, this was like the D, right? So by that theorem, this should be true, by that theorem. All right, so we're going to check this out. 24 minus 8, 16. Is that congruent to 4 minus 3? That's 1 mod 5. And this is true because 16 minus 1 equals 15. And 5 divides 15. Now let's look at part C. All right, so part C. 24 plus 8, is that congruent to 4 plus 3 mod 5? So this here, and the theorem would tell us it is, but we're verifying it. So this would be 32. Is that congruent to 7 mod 5? Got my parentheses here. And this would be true because 32 minus 7 is equal to 25, and 5 divides 25. Part D, multiplication. So we have 24 times 8, is that congruent to 4 times 3 mod 5, right? And that previous theorem would tell us these are true. This is a true congruence, but we're verifying it. So 24 times 8, that's 192. Is that congruent to 12 mod 5. And this is true because 192 minus 12 is 180, and 5 divides 180. And then last one, part E, we have 24 squared. Is that going to be congruent to 4 squared mod 5? This would be 576. Is that congruent to 16 mod 5? And this would be true because 576 minus 16 is 560, and 5 divides 560. Units digit. All right, so when an integer is written in ordinary notation, its units digit is the digit on the extreme right. So for example, if you have this integer here, 1,234, we know that the units digit is 4. The reason 4 is a units digit is because when 1,234 is written in expanded form, and it might have been a while since we've done something like this. This is what it would look like. You have 1,000 plus 2 times 100 plus 3 times 30 plus 4 times 1, right? There's your units. Units digit continued. The units digit of a number is the remainder obtained when that number is divided by 10, right? So using the 1,234 again, that's equal to 123 times 10 plus 4, or if you want to actually see the long division worked out, right? If we have 1,234 divided by 10, this would be 1 times 10, subtract, get 2, bring down the 3, 2 times 10, 20, subtract, have 3, bring down the 4, 3 times 10, 30, subtract, 4, there's your remainder 4. So in other words, the units digit of n is equal to n mod 10. So here's example 4. We're just going to find the units digit of the following. So we're not going to plug this into the calculator. Actually, honestly, depending on what type of calculator you have, you might actually crash your calculator. This is a very big number. So what we're going to do is we're going to use our modular arithmetic to find the units digit. So we're not trying to find the whole digit, the whole number. We just want that units digit of like 2 to the 75th power and so forth. So this is how we're going to do it. So for A, 2 to the 75th power, what I'm going to do is I'm going to start with 2 to the 0. Okay? And that's just 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And what I'm going to do is I'm going to keep writing these out until I get two numbers here on the right-hand side of the equation where the units digit is the same. 2 to the 4th, 16. 2 to the 5th, 32. And there I have it, 2, 2, the units digit. So this means if you just pull these two out off to the side, I have that 2 to the 5th is congruent to 2 to the 1st, or 2, mod 10, right? We're doing the units digit, so it's just going to be mod 10. So these are congruent. So this means then that 2 to the 75th power, I can rewrite this as 2 to the 5 times 15 power. Basically, the 5th here is the exponent. I want that to show up over here because then I can say that it's congruent to just 2. I can break it down. So right now I'm using an equal sign, right, to go from 2 to the 75th power. That's equal to 2 to the 5 times 15 power, which is also equal to 2 to the 5th, that value, to the 15th power. And now I'm going to switch to the congruencies. So this is now, I'm not going to use an equal sign. I'm going to say this is congruent to 2 to the 15, right? Because this part here in the parentheses, that's congruent to just 2. 15 keep. Okay, so then this is equal to 2 to the 5th times 3. So I'm using an equal sign there, which is equal to 2 to the 5th, that quantity cubed. Now I'm going to break down this 2 to the 5th, rewrite it as 2 mod m. Then we're going down here, so this is congruent to 2 cubed, okay, which is just equal to 8. And then you can't break this down any further, so it's just 8. And then because when we were doing these congruencies, it was with mod 10, so at the very end, you're going to have to put mod 10. Don't forget to put that there at the very end. And then you can't go any further, so you're done. So whatever this number is, I don't know what it is, but I know that its units digit is going to be 8. So we'll write down units digit is 8. All right, let's try part B. So for part B, we have 3 to the 2082nd power. So you're going to go 3 to the 0. That's 1. 3 to the 1st, 3. 3 squared, 9. 3 cubed, 27. 3 to the 4th, 81. And there's your units are aligned here. So you just stop until you have 2 of these numbers on the right have the same units. So now we can say that 3 to the 4th is congruent to 1 mod 10. So that's how we're going to reduce this. So then 3 to the 2082nd power is going to be equal to, I need to break this up, this exponent up, so that there's a 4, right? So that it matches this exponent here, so that I can reduce it to just 1. So you're going to have to do some scratch work somewhere on the side. I'm going to go over here. So I'm going to take this exponent, I'm going to divide by 4. So when I do that, I'm going to have 5, 2, and then 0. All right, and then the remainder is 2. So do a little long division on the side. So this 2082, I'm going to rewrite that as 4 times the 520 plus 2, plus that remainder. Okay, and I'm using the equal sign, so these are equals. This is also equal to, so I'm going to use equal sign again, 3 to the 4 times 520 exponent times 3 squared, just using your rules for exponents. And this is equal to, still using equal sign, 3 to the 4th to the 520 power times 3 squared, which I could probably just write that as 9. Okay, now I'm going to reduce this part with this, using this congruency. So this is going to be congruent, so I'm going to switch the notation to 1 to the 520th times 3 squared. Okay, well then 1 to any power is just 1, and then 3 squared is 9, which I can't break down any further. Mod 10, right? Mod 10. So make sure you put the mod 10 at the end there, and that's going to represent all the congruences we've used. So then your units digit is 9. So we're going to say units digit is 9. So regardless, I don't know what this total number was, very large number, but its units digit was the number 9. Check digit. So check digits are used to reduce errors in numbers found alongside barcodes. So these would include your universal product codes, UPCs, tracking numbers for shipping, book identification numbers like ISBNs. I'm going to focus on the universal product code. So retail products are identified by their universal product code, or UPC. The most common form of a UPC has 12 digits. I don't know why this is here, that's a typo. A UPC has 12 digits, the most common form. The first digit identifies the product category. The next 5 digits identify the manufacturer. The following 5 identify the particular product. And then the last digit is the check digit. So the check digit is determined by the following congruence here. This looks really messy, especially that left-hand side, right? And it's supposed to be congruent. The left-hand side is supposed to be congruent to 0 mod 10. But this looks really, really messy. So instead of like memorizing this formula or something, I'm going to break it up into steps. So step 1 is to add digits in positions 1, 3, 5, 7, 9, and 11. So you're going to add the digits in all of the odd positions, then multiply by 3. Step 2, add the result of step 1 to the sum of the digits in positions 2, 4, 6, 8, and 10. Notice this is not all of the even positions because we're not including position 12 because that's where your check digit is and that's what we're computing. And then step 3, the check digit is the units digit obtained when the result of step 2 is subtracted from a larger number that is a multiple of 10. Now I do have a note here because the maximum number that you can get in step 2 is going to be 207. That is the maximum number you can obtain in step 2. So for step 3, you could always use the number 210. Otherwise, try to find a smaller number that's a multiple of 10, but larger than the number that you got in step 2. And then there is an alternative formula. I'm not going to cover this. I just want to make you aware that there's an alternative. But in this class, we're just going to use the steps, step 1, 2, 3, for these problems. All right, so for example 5, the first 11 digits of the UPC for a granola bar is this here. I think the granola bar I was using was the Nature Valley one. And then we're going to calculate the check digit. Okay, so I'm just going to stretch this out a little bit. We have 0, 1, 6, 0, 0, 0, 2, 9, 5, 7, 9, and then your check digit. So this is like A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, 6, 7, 8, 9, 10, 11, and then 12. That's where your check digit is. So step 1 would be to add up all those odd positions. So the 0, 6, 0, 2, 5, and 9. So add up all the numbers occupied by the odd positions. That's 22. And then you're going to take that result and multiply by 3, so we get 66. That's step 1. Step 2, we're going to take that 66 and we're going to add to it the sum of the digits in positions 2, 4, 6, 8, and 10. So 1 plus 0 plus 9 plus 7. So this is going to be 66 plus 17, or 83. And then step 3, you can either use 210, or you're going to use a multiple of 10 that's larger than 83. So 100 will suffice. And you're subtracting the 83 from that number. Well, that's 17. And then that is going to be congruent to 7 mod 10. That is your units digit. So then 7 is the check number, the check digit. That's how you do it. And then we're done with this section, so I'll see you in the next one.